Yeah.
Correct.
Or like
Okay, cool.
cool. Hmm.
So what
Yeah,
is a space?
So vector space is a set that is equipped with a addition and a multiplication operation, and then all of the set and the operations satisfy a certain couple of axioms.
Okay.
Okay, so then wait, hold on, let me go back to annotate. So you have this set V, right? That's a set, right? And then you have a plus, which is defined on the V, and then you have a multiplication, which is defined on the V as well, right?
How come you put the multiplication in a dot? Is that on purpose?
I don't actually know. I think it's like by a convention.
Okay.
But I mean, I actually think that this like times is reserved for like Cartesian products type stuff, right? You know what I mean?
Okay.
And so we don't like, and also I think that's like there's other called the tensor product. It also looks like that. You know what I mean? Like that. X and
Or
so,
even with vectors, the cross product.
yeah, cross product. Yeah. So there's like a lot of crosses. That's why I think that's why they just like use a different symbol. I don't know.
Okay.
But to answer your question, I'm not sure. Sometimes there's good reasons for things. You know what I mean?
Yeah.
I read this like random article on like why localhost is 127.0.0.1. There's actually a reason, like in terms of like,
Yeah, cool.
there's actually a reason, which is kind of cool. But there's no, I don't know if
I don't write local, or I don't write that thing. I just write localhost, but you know.
Yeah, but that's the actual IP. Localhost is just a pointer to that IP. You know what I mean?
Yes.
But anyway, so what are the axioms? I guess that is a natural question to ask. And so I think they're just
before you do the axioms, I believe a vector space always has to be over a field.
Yeah, so then that brings me to the question of what is a field?
Wait, but maybe first clarify this for me. These two maps, they go from where to where?
Well, that is actually part of one of the axioms, right? Is that it's the field, the vector space has to be closed under addition and multiplication. That means that the result will this will be this map will plot, or sorry, how do I, I just deleted everything. That was not my intention. Okay, undo.
Yeah, cool.
Okay, so I believe what I was trying to draw was that this plus map, right, is defined as a map from V cross V. I haven't, yeah, sorry, I'm like a bit delirious apparently, but it's a map from V cross V to V. And so
the parentheses here?
Yeah, no parentheses necessary. And so the point is that basically you can think of it kind of like a normal addition, right? Like you add two numbers, you get obviously a number. That's like the barest thing that defines like an addition or a multiplication.
What does this notation mean though? Like what is plus?
Plus is a map.
What's a map? Like if a vector space is a set equipped with plus and times,
yeah,
are plus and times just sets?
Yeah, so we talked about this in some other session, but like the question is like, what is the, like, you know, if like what is the plus object? We said it's a map, and like what does that actually mean? Well, we can think of it like you like we can think of how, like, at the level of abstraction we care about, like the plus sign is actually like it's like a function, a black box. You put two inputs in and you get an output, right? But like, and that's the level, that's how like that is at the level of abstraction we usually deal with it at. But like, you know, what underlies that mathematically is like a different question, because like we can actually think of it like a like a set itself, right? And then there are ways to encode that map in that set, if that makes sense. You know what I mean?
Got you. What would be like a quick example of what this map is like? Like for spaced repetition purposes.
Yeah, so like it could be like a huge set of something that has the first element being the tuple, right, of two elements. Like for example, one, let's say we were talking about the real numbers for a second. The first element could be the two inputs, right? And then the second element could be the result.
You use
and then
numbers
like
in this case.
yeah,
I assume they stand like for vectors or whatever.
yeah, vectors or whatever. So yeah, but my point is that there would be this would be the first element in each set. This would be the second element. The first element would have two, and then the two like spots, and the second would actually, this would be a set. I don't know why I put parentheses. They should just really all be set brackets. But the point is that these two things together, or this could also be an ordered pair.
Because I think pretty
actually,
famously, you have to make sure that 1 + 2 = 3, but that also 2 + 1.
Yeah. So actually, that is a good point. So this first thing, 1, 2, would be an ordered pair. And ordered pairs are encoded in sets in like a different. There's another way to encode ordered pairs. And then the second element would be the result. And so would not necessarily, there would have to be another entry in this set that is like 2, 1 ordered pair with a 3, and then that's all in a set together. Then that would be a separate entity. And the point is like every single input and output of the function or the map is like included in this like large set, which is infinite.
Okay.
And that's also true for the multiplication. So it's really just 3 sets, but I believe the way that we think about it is like we just like, forget what's under it, and then we really treat it as a function.
Okay, got it. Small question. Is there a way of formulating maps generally in terms of sets? Like you gave this example here, but I believe there's like an equation or something. Like a map is an element, like F, general map, element of the power set of, what is it? V cross V, I believe. No. Wait, what is it? No, V cross V times V. In this case, no, V cross V. Okay, bad parentheses, but I don't know. I guess I just saw this somewhere. Maybe it's right or wrong.
I think this is yeah, maybe I'm I think this is pretty close. The point is that we actually just want to have all combinations of order pairs here, and all combinations of like outputs here, like, and then we like combine them in all possible ways. And so like I think the idea of having like this should actually just be like the symbol for an ordered pair. This should be like the symbol for the vector space. And then if we cross them, we create a power set of those, of all possible inputs and outputs, then we would say that F is we could say that F is the element of that. But then the other thing that is important about that defining function map in this way is that maps have other axioms than just including certain inputs and outputs, right? Like to be a function, you have to have one output for every specific input. And so you have to be like such that, and then you'd have to state things about the combinations that show up here.
But maybe the power set guarantees that already.
I don't believe so, because if you have like all combinations of like one of ordered pairs and outputs here, you'll end up with like 1 × 1 and then like every single thing here. And so you actually have to sort out infinite amounts of garbage to get a function. You know what I mean?
No, yeah, that actually makes a lot of sense. So this is maybe type theory, correct? It's like saying that a function is of type blah blah blah, but then in practice, it's going to end up being a subset of that type.
Yeah, I believe so. That would be like I wonder like something about like, I don't know what the abstract version of a like I don't even understand what the notion of like a function that could have multiple outputs for each input would be. But the point is, if that existed, then a function would be like a subset of that type.
Yes.
But I don't know if we have that notion in math, because it doesn't seem that I don't know what the use would be. Maybe there is, just I haven't been.
Maybe a graph or something.
Yeah.
Since graphs don't care about like input and output.
Oh, right. That could be a good one, right? Yeah. It could be like that could be like a way to encode a graph. That's cool. Okay, but
back
and
to
so
spaces.
as going back to vector spaces, right? A vector space is a set equipped with these two operations, right?
Oh, wait, what's
And
the second one? I feel that's pretty.
oh yeah, the second one is also defined in the same analogous way. And the other thing is that like important to realize is that
Oh, hang on.
oh, interesting. Right, yeah, I forget. That is that's not actually right. Okay, I erased everything again. Um, okay, so yeah, this is actually scalar multiplication. It is definitely not vector multiplication, even though the notion of vector multiplication exists in most vector spaces. So it actually would not be v cross v. It is
Wait, but we mean vector multiplication. Like technically this is vector multiplication. It takes in two vectors and it returns a vector.
well, we call that addition, but my point is like the idea of vector multiplication is more is some structure that you can add on, but that's what I'm talking about with that, like, you know, we all
But
commonly
that's
push
actually
it.
a good question. Like eventually you're right. There will be a times that's v cross v to v.
Yeah,
Plus is also v times v to v. So like why is this one plus and this one times?
yeah, exactly. I think that's like here, like that is a really good question. Because but here's like my point philosophically is that we've actually said pretty little about this like thing by just like stating its domain, right? It can function in any way. This like operation as like a relation of two variables, well, it's not a relation, but it's like my point is like a map of two variables back to the original set. It's like that could be addition, multiplication,
Yes.
subtraction. Like we
I
haven't
don't know
said
about
anything.
subtraction because it does have the restrictions like Caney or whatever, like commutative, associative, neutral, and
Right,
inverse.
that's my point is that we haven't even talked about those yet. You know what
Yeah.
I mean? And so
Yeah.
like right now we haven't even introduced how this thing is going to function. And so it could be anything. But I think that like canny thing is actually like a pretty strong restriction, and it like lends itself to be called addition, right? Like um yeah, like
No,
that
you think that just Caney calls it makes it addition?
I
Yeah.
believe so. Well, we can investigate that later.
Yeah.
But maybe like if I look, I actually these specific axioms escape me. I understand like their gist, and I'd have to we could check very quickly, and I think we could come to a conclusion very quickly as to like whether or not.
Yeah. But no, I would be very, I mean, I feel like this is a common question in math where like you are given just a random thing like plus, which is super general, and then you restrict it. And then sometimes it's going to be restricted all the way down to a single choice. But then other times it won't.
Oh, well, definitely. There's many choices of addition, I believe.
Okay, so you believe there it isn't a single choice. Okay.
Yeah, no, it's not trivial, but I'm saying that like I think like remember like okay, well, like in some other like lecture, Mr. Frederick Schuler introduces the notion of a metric, right? And or distance. It's called distance or metric. I think it's called metric. Um and he says like three things that are relatively interesting about the metric. He says one, like it's commutative, right? So AB
Yeah.
equals BA, right?
Oh,
Which
yeah.
kind of
And then something about the triangle inequality or something.
yeah. The second thing he says is that the distance between A and B has to be greater than 0,
Yeah.
or A equals B. You know what I mean?
Okay,
And the
yeah.
third is that the triangle inequality, which I'm not going to write out,
Oh,
but my point is, it's just like a really interesting thing to me that like what we're kind of trying to capture here is the notion of a distance. You know what I mean?
yeah.
And these are the three things that kind of encode distance. You know what I mean? Like anything else can vary. Like there's nothing else that's fundamental except for these three things, right? And so my point is, right? Does that make sense? Like the
But you
like
still have
notion.
choice. You still have
There's
choice.
so many choices,
Okay.
but these are the like these three things like kind of capture the notion of a distance, like the abstract notion, right?
You
And I
can't
guess
say a distance. Okay, I guess it depends what a distance you mean here. Like a single distance, no, but of a distance, as in like all possible
yeah,
distances you can. Okay, sure.
captures the note, yeah, of any specific distance you pick, right?
Okay.
I'd say if it violates one of these rules, like common sense wise, we wouldn't call that a distance. Imagine you had like a distance that, it's actually kind of weird. Like maybe I could come up with an example where it's like
What if
the
A
distance,
B?
including hills or something, you know what I mean? The hill distance or something.
Oh
Then
my
it
God.
wouldn't be
Does he give the example with Paris or something? The Paris
yeah,
train network. Was that in the lecture that
that
if you,
was, yeah.
okay, yeah, the Paris train network.
But that one does obey the things, right? Like it does
Yeah,
obey
yeah,
them.
yeah.
But anyway, so my point was with this canny thing, like it's not that there are choices, right? But my point is like I think it fundamentally encodes the notion of a addition pretty well. Like you know what I
Addition.
mean?
I think it's addition, multiplication, other things. Like go through the list, right? Commutative,
Okay.
associative. I mean, okay, this is for later anyways.
Yeah, let's do that later. Okay, and so this is a scalar multiplication, so it's actually going to be R cross V, and it's going to go
Oh,
back
is it
to V.
always R?
Yeah, I think so.
I
Or
believe
maybe,
it's written F before. F cross V to V.
oh, what is F?
Like a field or something.
Oh, interesting. So hmm.
Like
Yeah, I don't even
I've heard
know.
like there's like real vector spaces and complex vector spaces. And then they write F just like as the general case.
Interesting. Okay, well, I kind of forget that,
Yeah.
or like I actually don't know that, but it seems reasonably that like there could be complex vector spaces, and then you wouldn't have R. You need Oh, my toy just broke and spilled flour all over the place. I gotta clean that up. I'll be back in 1 second.
Yeah, go.
So,
Rip.
okay, I'm back. Actually, no, I need to get my trackpad here. That should be fine. I'll do it later. Okay, well, yeah. So I mean, it seems likely that you could put C instead of R.
Okay, cool.
So we'll call it F.
Okay, F.
My friend F. Okay, and then my point is, so I guess like the natural question that follows this is like, what are these? Like what did they actually? How did they function? You know what I mean?
The F or the functions here?
The functions themselves.
Okay. Because I guess, yeah, you haven't looked at fields yet.
What? Yeah, I actually don't know what that is.
Okay, cool.
Max. Yeah, so let's write them down. Axioms of vector spaces. Good. So we have a bunch that talk about so I think most axioms, like the axioms, really make statements about how the operations function.
Okay. Or would it be correct to say restricting, like straight up restricting, or expanding as well?
What do you mean by restricting or expanding?
Like we talked about how like plus had like a billion different choices, but some of them are going to be like pretty stupid. So
oh yeah, it's I believe they're all restrictions.
okay, cool.
Okay, so the first one are statements about the addition thing, and so those are canny, right? I like canny. So this is basically saying that V plus, or we should actually just pick W V, like lowercase things, yeah, like V and so.
But what does it stand for, by the way?
So yeah, this one stands for commutativity.
Okay.
The commutative property or whatever. It's basically saying that V plus W equals W plus V, right? If you think about, well, so this holds for addition, right? And obviously this all like imagine, I'm just like saying we'll go through this list and we'll see what does these discount. And clearly it discounts subtraction and division, right? And so we kind of now we've decided that this cannot be subtraction or division like things, like the notion of subtraction or division doesn't work with this anymore.
They are not commutative, subtraction and division.
Yeah.
Okay.
But
But addition
and then
multiplication, yeah.
Yeah, I agree with that. And the second one is that, oh, this is associativity. So it's V plus, I mean, yeah, so I mean, we know V plus W plus Z equals V plus W plus Z. And I'm going to move around the brackets here.
Okay.
And then the second one is, yeah, the brackets are now here, right? And so it's to say that no matter how you group it, it's not going to change the outcome. And that also would work for multiplication, like this notion of addition and multiplication both function here. The next one is that.
Wait, what about division and subtraction? Or yeah.
Yeah, again, so I don't, it doesn't work, right? There's like, does 6 or does 12 divided by 3 divided by 2 equal 12 divided by 3 divided by 2?
You couldn't pick 4.
Yeah, I should have picked something better, but I tried to, but I failed. I was actually thinking about it. But I guess if you put the 2 first, it would have worked. But yeah, but my point is it doesn't work, right? Because
2 equals,
this would be 4, and then that would be 2 at the end. And then here that would be 12 divided by 1.5, which is some other number. It's like
wait, what about matrix multiplication?
Matrix multiplication. Well, yeah, matrix multiplication functions in both these situations. Yeah.
Okay.
And then yeah, but I think matrix multiplication is yeah, it's an interesting one for sure. Okay, but the next one is the existence of a negative element. So there exists a 0 basically like for all V, right?
Wait, will multiplication of 2 vectors work?
What does that mean? Or like multiplication of 2 vectors, like component wise?
Wait, hang on. Because I think at this point we've just said that V is like whatever vector possible. Like we haven't named a specific one. Yeah.
Yeah, but we've been dealing with the notion of abstract. Like we've been pretty lazy with that. You know what I mean?
True.
Because like, like if we could just like say that we're dealing with like R2 for all these, then it would be like interesting. Like we could just use that as an example.
Sure. R2. And then what's multiplication on R2? That goes from R2 across R2 to R.
Yeah, it could be like component wise multiplication. And in that case, like can C and A are both satisfied.
You're right. Yeah, for component wise. Okay.
But most of
the time, the cross means like a cross product. Oh, yeah. Which doesn't exist on R2 though.
Yeah, because I think like I was thinking like, what is the cross product again? Oh yeah. Wait, but doesn't this give you a number, like one number?
This is the dot product.
Like the cross. Wait, what does the cross product actually give you?
It's like vector? 2 vectors, it gives you the vector that's orthogonal or whatever that, or perpendicular.
Oh, fascinating.
Yeah.
Yeah. Okay.
So very useful for like computational whatever.
Yeah, I believe that would be very useful. Okay, well, yeah, so I mean, well, let's continue through the CA, like the canny stuff. And I don't know about like, I'm not like very knowledgeable on the like the random things they could do. Like the whole idea of a function space, just like I remember they giving that to me in my linear algebra course. And I thought that was just like a random example, like, haha, you were able to make this funny thing, you know what I mean? But then it turns out to actually have applications. And I kind of like, and it didn't sit well with me. For some reason, I just don't like it. Like, or I'm not able to work with it naturally. And so I guess my point is like, I'm not super good at like dealing with these like super abstract vector spaces. but we can think about these like things as we go. Okay, so then the existence of a negative element is pretty simple. Basically
Hang on, I think
saying
it stands for neutral.
neutral, yeah. Inverse is negative. Yeah, you're right. So it's for all v element v, right? There exists an, we call this thing with this funny symbol 0 such that v plus 0 equals v. Yes, it's like a neutral element. It's kind of nice. And so now this is clearly the case, not the case. This would clearly not work for multiplication anymore, or scalar, like, multiplication defined on R, for example, right? Because
but scalar multiplication. That's a bit of a weird example.
I mean, also it's weird. Well, certainly it's not actually, the thing I just said was very fallacious because this is just a funny symbol for this thing, right? That it, and so the question is, does it exist? You know what I mean? Like, and so I guess even with multiplication, right? Like it could exist, but we would have to assign 1 to this funny symbol. You know what I mean?
Yeah.
Because 1 is the neutral element for multiplication. So there, we haven't violated anything yet, but I believe we will get into a contradiction later. Like if you have the 0 symbol and it's used in 2 different contexts, it won't work. Okay. But anyways, so for nothing to say about that right now. The point is we're saying that this funny symbol exists. Okay. And then inverse says for all v, there exists negative v elements of v such that v plus negative v equals the neutral element. And then also it's like very important to like notice that these things are like in a bracket. Like it's not, there's no such thing as negative, like a minus. We haven't defined that. You know what I mean? So this is really just like a symbol for like a, for one vector. And also important that it's just like these axioms don't say anything about how these symbols behave. They just assert their existence. And then we just like find that out of that. These symbols are like invariant, you know what I mean? Of per element. It's just like you know what I mean? Does that make sense?
Yeah.
Okay. So that's like statements about how addition works. And then there's statements about how multiplication works. I'm just going to do them very quickly. So the point is 0 dot v equals v. Then we have 1 times v.
Axioms or what?
Yeah, these are axioms.
They're axioms, but no, they're not axioms.
These are multiplications.
Axioms. Oh, you're talking about the one. Okay, this is separate from addition. This is the next ones.
Yeah. I think there's only canny. Am I missing any?
Yeah. Well, yeah. No, there's then the ones for multiplication or scalar multiplication. You're correct.
Yeah. Yeah, and so these are statements about how and so this is not that there exists, it's an assertion about how this element behaves. And it's to say that this neutral element times v for any scalar number, or for any if you plug in the neutral element here. Oh no, this is a real number, right? This is the actual 0 from the real numbers or the complex field. Yeah.
Well, with the field, yeah.
Yeah. Complex numbers, but so my point is there's 0 and 1 here.
Okay, got you. Oh, so okay, 0 and 1 statements about 0.
Sorry. Yeah, and then actually, sorry, this is, and I have it wrong. This is 0 times 1 equals the neutral element. So this is now we're talking about the vector space again, right? Okay. So I should have put like some way to denote the neutral element versus 0. Yeah, it is very confusing, like the fact that they you know what I mean? Yeah. And so I'm going to put a dot for anytime it's a neutral element of the vector field. And then
but it's never going to be 0 because 0 is a specific example if you pick the real numbers.
Exactly, right? Yeah, exactly. And so it's actually a pretty confusing notation, but I'm not going to hate.
Oh, by the way, do you want me to give like a really quick explanation to fields later? Like after
Sure,
the
yeah, I'm curious.
okay.
Okay, yeah, so we make statements about how this is actually a statement about how the neutral element functions, you know what I mean? And yeah, these are statements about how vector multiplication functions. And then we have statements about basically this concept called linearity. I'm gonna
Yes,
erase.
that's an important one. Wait, are we finished like a big explanation about what vector spaces are, and now you're moving on?
No, because there's actually two more axioms that we need to satisfy to have a vector
wait,
space.
not linearity. I think you mean distributivity.
Oh, yeah, I think like these are pretty related notions, like the idea of being like linear. Or actually maybe I'm not like quoting this right. Like maybe the notion of it of being linear is actually like localized to maps, you know what I mean?
Yeah,
But I think it's like actually pretty you know what's interesting? I think there's like a parallel here. Do you mind if I just grab water really quickly? Okay. Damn, I really like that like fidget toy I had that was filled with flour and is now like under my keyboard, which is incredibly upsetting.
Yeah.
No, get out of there. I hope that doesn't like ruin my keyboard. That would suck. Maybe I need like just like a compressed air blower or something to get it out.
Is this the Mac, the new Mac? Fancy.
Yeah. Well, basically what happened is I can show you.
Oh, that's sad. Rip.
Well, actually for it's on the touchpad, so it doesn't matter, right?
Okay.
The touchpad doesn't matter
Wait,
because
it's not. Your Mac doesn't have like a touchpad?
well, the point is like the touchpad, it's actually not, there's no physical mechanism there, believe it or not.
Okay.
Um,
Yeah, it's
and
just
so it's actually just
something.
it's like a vibrator, yeah. And so my point is if flour gets stuck in that notch, I don't care, but like all the keys are physical mechanisms, and so
Yeah.
that sucks. But yeah, I'll have to clean it up after. Okay, but I digress. Okay, so there's two more axioms that we have to talk about. Yeah, the distributive axioms. Oh, and basically this is a statement about the combination of addition and multiplication. Is to say that C times V plus W equals CV plus CW.
What's C?
C is a member of the field. So it's like actually there's like a dot hiding here. And I think like from now on, if there's no symbol in between things, we just like assume that it's the multiplication. And then the other one is V plus W times C equals CW plus CV plus CW.
Oh, so for the left hand and right hand side of the parentheses.
Yeah, those are the two.
Okay.
Well, actually, I think one is actually a statement that you can pull you can put the multiplication in here. You know what I mean? You can put the multiplication in here. And for this one, it's actually, I think, a bit different. It's saying the addition can come out.
Oh, interesting. Okay. That makes sense.
Or maybe it is the exact same thing. I wonder why these are different. Let me just look up another example of a vector space for 1 second. Or like, I'm gonna grab someone else's definition.
Sure.
Oh, this one. Talk about monoids. I don't need to know that. Wait, but yeah. let's like not do this right now, but I guess so. So my point is, I guess the explanation of a vector space is if you satisfy all those conditions that we just laid out, then you have a vector space. And again, most of them are just statements about those two operations, right? And
Okay.
so yeah, it's kind of like choose a set and then choose the two operations, and if they satisfy all those things, then you have a vector space.
Okay, sounds good. Do you have examples of vector spaces?
Yeah. So
this is probably the most critical part. Actually, do you mind if I explain fields super quickly first?
yeah.
Okay, yeah. So basically, whenever I hear the word vector field, I always think that's technically inaccurate because you should always say vector field over a field F, because of the fact that like for defining a vector field, you need the times, which is F cross V to V. So you need to have like to have an F there beforehand. 99% of the time, it's just going to be R or C, but technically nothing is stopping it from being other fields. But that's quite weird. So yeah, always R or C. Now, as for what a field actually is, it's literally just exactly what you expect numbers to be. Like you can equip the rationals with your intuitive multiplication and intuitive addition, and that's a field. You can equip the rationals with your intuitive addition and intuitive multiplication. That's a field. In theory, actually has like axioms of its own. It has the same k for the plus, since plus times from R to R, or the field to field to field. And actually very nicely, same thing with the times. It's also k so very easy to remember. And then there's the last one about distribution between them, similar to the other distributions, but I tend to forget it. But literally what a field is what you expect numbers to be.
Oh, interesting.
There are like weird examples of these things called finite fields, which are actually fascinating. Where you have like a few field elements and they still satisfy k and k, but they have like only 3 or 4 or 5 elements or a finite amount.
Yeah, it could be like modular arithmetic.
Exactly. Modular arithmetics is squarely under fields. So it's quite interesting. But yeah, the big disclaimer for me is whenever I hear vector field, like that is wrong. In my head, I should always say vector field over what? Over R, over C. I mean, those are the main.
Fascinating. Yeah, but like it just, that is very interesting. Okay.
Examples. Oh my God, you hear the quote in the video? I'm going to take advice from the Prince Machiavelli. What is it? Have no mercy or something. Do things that are cruel. I don't know, something like that.
Yeah, I think that he got done poorly by history because the book's actually relatively tame. So I have it here.
Hey, the Prince. I think so too. I think the book is relatively like not like the point is it was like he wasn't like an evil person. He was just like commenting. And it was actually, I think, supposed to be a guide or something, how not to rule a country or something. I'm not sure.
No, I mean, I think it's supposed to be like a guide of how to rule a country, right?
No, because it does. It explains like, oh, be brutal. Like it's purposefully like very dictator-ish. But Machiavelli like did not believe in that stuff.
No. I think you're wrong. I believe you're correct. You're just wrong. Like if you read the introduction, it's basically like or you read like actually basically the story of the book was that he got deposed from power somehow, like he got replaced, and then he was like trying to curry favor again, right? And so he wrote this manuscript of this book as like a gift to like the new ruler, as like all the lessons he learned being an advisor for like the past like 20 years or something. And so it was all supposed to be legit. And there's like, but the point is like, if you read the book, I'm like halfway into it. It's like literally very short. It's like 100 pages. But the point is, if you read the book, most of it is like just practical advice of like, should you live in the country you conquer, or should like, how do you keep territory? And you know what I mean? Like, nice. What about like successors and like, how should you treat, neighboring countries and stuff? And then like he says certain things that are like practical yet cruel. but it's just like he's just like saying things that are like accurate. You know what I mean?
Yeah.
It's not like he's like particularly cruel. He's like saying like, if you piss off a group, you should like exterminate them instead of I think it's pretty messed up. That was pretty messed up, but it's also accurate. So I don't know. Anyway, my point is like, he's not evil. I think he just practical.
I think what happened is that there's this video on YouTube by CGP Grey called Rules for Rulers, and it covers like a very similar topic, like what should rulers.
I believe it's very similar. Yeah.
Yeah. The point is, imagine 300 years from now, people are like, "Oh, CGP Grey, bro, he was like trying to help out Kim Jong-un by like helping." Like, what the fuck? No, he wasn't. Like, he was just commenting on, like, at this moment, CGP Grey is commenting on like the way that the world works. And I believe like Machiavelli was doing the exact same. Like he wasn't actually intending for any prince to use this and like rule shit and stuff. Except I wasn't aware of that story where he gave the gift creating favor. I'm very surprised to hear that.
No, I think he was. I think like I think actually it's not the case. I think your notion may be incorrect in the sense that I believe this is all just like advice of him. Like he wasn't like an academic study. It was like practical advice. But yeah, like I don't like, I think also, yeah, I don't know. Like you might want to read more into it. I mean, maybe I'm wrong too.
Yes,
I'm like, I would have to be
wrong. That may, this is from like many years ago, just hearing something. So I'm probably wrong.
Yeah. Okay. But yeah, I mean, that is anyway, you satisfy those axioms, you get a vector space, right? And then I mean, I could also talk about linear maps.
Oh, wait, the reason I came up with the princess for examples and the funny quote in the video where it's like,
oh, right, examples.
I'm not going to give a single intuitive example.
Right, because yeah, certain things have to be cruel, but done on purpose. Okay. Yeah, so some examples are, well, the real numbers equipped with plus that we know, and
very careful with the real numbers.
Multiplication.
No, that's not a vector space. I mean, it is a vector space, but it's just so weird because of many reasons.
Well, I'm curious what you think the weird things are.
The weird things are that a vector space always has to be over a field. And in this case, your field is going to be R.
Yeah.
Times. And your vector space is going to be R. And so the multiplication goes from FV to V.
Yeah.
Which F is like a totally different thing. It has nothing to do with V.
But but it still works, right?
Yeah, it still works. It's just confusing because then people think that multiplication is always from R to R, which is not true.
Yeah, I agree.
If you can explain, including the nuances, then it's a great example. But for beginners,
yeah, I mean, well, but like I understand.
Okay.
That, like for example, but yeah, I mean that I understand your hesitance towards that as well. Okay, now a better example maybe.
Oh, wait, but the reason I always drew this as a dot is exactly for the reason of like clarifying whether it was like the multiplication on the field or multiplication on the.
Yeah, that's right. Okay. Let's also, I mean, the better example is, how do you denote matrices anyways? Like the set of matrices.
I don't know.
R cross R cross R.
Oh,
I don't know, like something like that. My point is is it like R11 or something, R22 or something?
Yeah, that was a weird one. Maybe, you know what, explain the R. R2 is a bit easier to tell apart since the field is just R. Maybe you can explain R as an example if you want. Oh, maybe that's how you do matrices.
Yeah, but my point is R22 equipped with addition element-wise. Okay, element-wise addition, and this dot being matrix multiplication is a vector space.
What's the underlying field?
It's still going to be R.
Okay, cool.
And it's just like an interesting thing that the matrix multiplication kind of functions like addition that we were typically familiar with.
Okay.
Yeah,
that's an example of a vector space. Cool.
Yeah. another one is
I mean, you can tell me that it does Kani Adu or whatever,
yeah,
that it satisfies that, and I can take your word.
yeah. I will take my word. I would show you, but
Too much
I
work.
don't know if that's necessary. The next, another thing is like functions can behave like vector spaces if you have like a set of maps, like the maps could be from like R to R or whatever, right? But if you do addition as like function addition, that means like you just, so I'd say like, let me just say f plus f
Yes,
equals,
addition. F evaluated at X or whatever.
yeah, f, I mean, I don't know how to say it. Like yeah, f plus, or f plus g of x. Oh, you're right, that's better. F of x plus g of x, right? And then same f times g of x
No, no,
equals,
no, 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 no.
oh right, yeah, I keep messing this up over and over again.
Scalar multi. It's because of
Yeah,
the
it's scalar
example with
multiplication.
R. I'm telling you, and R like making you think that
Oh,
multiplication is R cross R when it's
yeah,
scalar.
but my point is f lambda
Lambda
f of
standard one.
equals, oh, I mean lambda, where should lambda be here?
Inside, like lambda.
Yeah, exactly, that's my point. um f of lambda x equals lambda f of x, which is, it seems like trivial. It's just like so simple that it must be trivial, but
Well, you see, I actually have a problem with this.
yeah, what's your problem?
What does any of this have to do with a set V, a plus, a scalar multiplication, and then Kani Adu? Like,
Oh,
I don't see the relation.
well, so imagine we have a set of like of all maps, right?
Uh-huh.
Right, like let's say from R to R, that was the example I was given, but we're talking about x's to make it like nice, right? Then I say let's define the plus, right? F plus g. This is how you add two vectors to get a new function. You know what I mean? And
Okay.
that's our plus. And then this multiplication, this is how we define scalar multiplication here.
Ooh, okay. So this is a definition. This isn't like a condition.
No, this is a definition.
Okay.
We're saying this is how our plus works and how our multiplication works.
But
And
why
then
did you say
this,
linearity when you describe this? If it was more just like,
I actually didn't mean to say that if I did say that.
okay.
Yeah, this isn't really much about linearity, more than just like this is an example of a vector space.
Okay.
Yeah.
And then all the functions are like the set of all possible functions are the set V, or is the set
Yeah.
V, and then plus is the addition. Fascinating. Okay.
Yeah.
This is a vector
There.
space over R, I'm guessing.
Yeah.
Okay. Sometimes people use
There.
multiplication, I see, to signify the field that it's over. I don't know.
Yeah. And then, I mean, there's more than that.
Yeah, seems legit. Seems like you've explained.
Seems legit. There's a seems legit.
Here, I have
Okay.
a series of questions to go into the next topic.
Yeah.
So I've often seen linear algebra described as the study of vector spaces. No, not vector. Oh shit, actually, that's sort of an important question. What the hell is a vector?
Vector literally just means the member of the set we defined, as long as the set, these axioms are satisfied. And so there's like a lot of connotations around vectors because like these damn engineers keep doing engine like but there's actually nothing, like there's like saying something is a vector does not imply much about it at all, except for the fact that it's a member of the set that we defined as a vector space. Yeah.
So this is a vector.
Yeah, that would be vector, that function itself.
This is a vector, like an example of a matrix in this system.
Yeah, it would be a vector.
Is
It's
this
only a vector. Well, it depends with respect to what vector space you have.
Let's go. Correct answer. Bro, this notation, I really don't like it. but whatever.
It
Yes.
hates like every practical thing. No, I'm just kidding.
Okay.
Mathematicians.
So vectors have been explained. Mm. Oh yes, I had a series of questions to lead you into a potential next topic. So
Yeah.
I've also always seen, or I've seen the entirety of linear algebra being compressed down into this one sentence. Linear algebra is the study of vector spaces and their structure preserving maps.
Yep.
So this is the next topic. What is the structure preserving map? Preserving map on vector spaces. What does that mean? And that's the question.
Vector space and structure. Oh yeah, okay. So well, we talked about what a vector space was, so we kind of know what that is, right? But a structure preserving map is what's a well, I mean, so you think about what is the structure of a vector space. It's the function of those operations that we just defined, right? And so a map from, yeah, so I believe like this is related to the concept of linearity in the sense that a map that respects linearity is structure preserving. And then now we have to ask the question of what does that mean, right?
Well, first, why do I trust that statement? Did mathematicians just declare that linearity preserves structure? Or is there a way that I can look at the definition of a vector space with including the k-need and then derive, oh, for some other vector space, W, for a map F to preserve structure, what restrictions must it have? And then that's how you come up with linearity.
Sorry, can you restate your question one more time?
So you said like structure preserving map on vector spaces is linearity, correct? You said that?
Yeah. Yeah.
How can I trust that statement? Why
Yeah.
linearity
and so that's what I mentioned. So like this structure preserving thing, it's actually with respect to the function of scalar addition and multiplication. So if scalar addition and multiplication continues to function in the same way under a map, then like that is structure preserving. Whereas if you like pipe a variable through a map, or you pipe a vector space through a map, right? And you've messed up the
interesting.
You've messed up the function of addition and scalar multiplication, then that's not structure preserving. Okay.
Wait,
so
can you clarify that for me? Like if this is a vector space,
yeah,
and you said piped. So okay, like you have the pipeline, and then you have an F that's not structure preserve, or that is or is not structure preserving. What's the statement? Are you saying that if F is linear, the resulting blah, blah, blah is also guaranteed to be a vector space? Like, yeah, this is the topic of how can I trust what you're saying? And then feel free to think here for a sec.
Yeah, so like a few disparate like mental models I have that are kind of like floating around my mind, and maybe I can stitch them all together into like a coherent answer. One thing we can think about is like the idea of looking at how the map changes the vector space. And so like imagine your vector space was like you could visualize it somehow. Just imagine there's a way to visualize your vector space, right?
Okay.
You have like vectors that are just chilling, like I don't know how to do this in like an abstract way. This is hard. But yeah, so if I was gonna get like concrete, like we could say that, like imagine we had like vectors that point like all over, like, you know what I mean, to like all these different places in this like two-dimensional graphical vector thing.
Sure.
like we can imagine that we take all the, like if we if we took a map to a different, I gotta think about.
Wait, hang on, but this is just R2, right? So you're saying, imagine you start off with R2
Yeah.
and then you
Yeah. Well, okay, well, I mean, like I know that so something about this whole, like, so we have this map F, right? F takes vectors. Just to make sure that we understand that F doesn't necessarily, like, what is F, right? Like, what is a map for like, okay, like we're talking about this map, but like what does it actually look like? So we can talk about some of its things. So a structure preserving map takes something from one vector space to another vector space.
wait, a structure preserving map? Yes.
No, like yeah, well, a structure preserving map is so structure preserving map is a special type of map, right? You understand that, like when we're talking about maps in linear algebra, we're talking about maps that take, right? F takes elements from a vector space and maps them somewhere else, right? And I think like one thing you just have to like accept, I guess, kind of, is that like if you are taking things from something that like, or I don't know like how we can rationalize this, but my point is like this map should be mapping to another vector space. It doesn't have to be the same one, but it has to be mapping to a vector space. Now, why is that the case?
Wait, but no, but you can easily come up with a map that takes in a vector space and then spits out garbage.
Yeah, for sure. But like, is that structure preserving is the question, right?
Well, I mean, not, I guess.
Well, then the answer is, why is it not? For me, like I think the one notion of like structure, like one thing you want to maintain in math is that like if it is structure preserving, you should be able to invert it. Like that is just like that is usually a true statement about most structure preserving maps.
Okay.
Like that is not to say that you have to find the inverse transformation, but it has to be in principle invertible. That is to say, like all the structure information to transformed in the map should still be there at the end, like all that structure information. And so if you invert it, then like it means it's still there. And so
but hang on, isn't this because we talked like about last week or a few weeks ago with sets? Then the structure preserving thing for sets was cardinality, right?
Yeah.
And it was uniquely defined by inverses. So if an inverse exists, then cardinality is the same for the two sets or something.
Yeah, something like that.
Okay, but blah blah blah. Okay, this is some other thing. But back to this topic. You're saying an inverse must exist, but there must also be additional conditions, right?
Yeah, right. Yeah, definitely.
What are those?
I'm just thinking about like what are the fundamental things about a vector space that we have to like make sure are correct for like us to say something about like a.
You mean about a linear map or about a vector space?
Well, I get the question that we're trying to answer is, why is a linear map structure preserving, right?
Yeah.
I guess we could answer that question by like laying out what a linear map is, and then talking about why.
I don't know. I feel that if you start with a vector space and you ask yourself the question, they're all possible maps F, right? Some of them are going to spit out a vector space and some of them are not. Some of them are going to spit out garbage.
Yeah.
I can ask the question, what restrictions must I put on F to guarantee that there is no garbage and that every single output is a true vector space somehow? And I believe,
but like, I guess my point is like, why even does it have to spit out a vector at the end? Is that really like a, like, you know, because like I guess you could like imagine that we talked about, and like, remember in topology, topological manifolds, we were talking about the fact that there's like it's locally homeomorphic to Rn. And so like that's an example of how you can have a homeomorphism, which is like the structure preserving map to something that isn't necessarily the same thing that you started with. You know what I mean? Like maybe this is like home, maybe we don't need to map to like how come we have to map to a vector space here? You know what I mean? I guess that's my question, even like your question kind of prompted with me. You know what I mean?
Yeah.
What do you think? Do you have an answer?
Well, okay, hang on. If we restart from the very basic, let's say we have a vector space V.
Yeah.
And we have a function F.
Yeah.
This function, I've said nothing about it. It could spit out garbage. It could be a good function. It could be a bad function. I don't care. This could be like from any kind of function. Some functions are going to spit out vector spaces and some functions are not.
Yeah.
What restrictions must I put on F, like additional requirements on F, so that it's guaranteed that any inputted vector space will output a vector space? And I believe those conditions to be the linearity conditions, which is that, what is it? F of A plus B is equal to F of A plus F of B, and lambda of A, F of lambda A is equal to lambda F of A. I believe that if your map is able to satisfy these two conditions, it's guaranteed to output a vector space. And if it fails, it's going to output garbage.
I'll have to think about that again. I believe that is true. I was like trying to grasp how that's true. That's my point. I guess my whole point was like how does that follow was like isn't still not clear to me right now.
Okay.
Like it does
feel true.
I don't think it intuitively feels true, but the ingredients for it to be true are certainly there, because I see within these two constraints, I see things very similar to the axioms that we put on it, right? Okay. However, I'm not convinced of your claim by like just you saying it. You know what I mean?
Okay.
That is very interesting. Yeah, I'll have to ponder on this for a bit.
Okay.
By the way, I'm a bit out of juice right now. Do you want to like pause and pick it up another day?
Yes.
Because there's like way more to talk about than just this.
How about this? I think it's a good idea to attempt to explain covectors, even if you don't feel comfortable doing it for like 5 minutes or something.
Let's do that. Yeah.
When you re-listen to the lecture, your mind will be prepared to accept information.
Yeah. So so covectors, I think are, well, actually, can I just ask you the question that was like kind of not sitting right with me in the first place? So I understand covectors is a map. So a covector is a map from a vector that maps a vector to the field that it's like on. And so an example would be like we take the vector space equal to R2, right? Then a covector, right? Could just be the length of V, right? That's like an example of a covector. Okay. The only restriction is that it has to map from V to R, right? And so anything that could take a V to an R is a covector, right?
I believe it does also need to be a linear map, but that is
linear map
the outside of what is needed.
Right. And in that case, linear, oh, right. That is a really good point, that it has to be a linear map. But in this situation, that does actually work. So if you check it out, the point is if you add two vectors, you're going to get a vector, which the distance is going to be the sum of the two. And then same thing with scalar multiplication, it's going to not change it. It's going to change the distance linearly, which is kind of cool, I suppose. Well, anyway, and so a tensor is defined as a map, right? a map
Mhm.
from that eats some vectors, right? Some vectors, right? Dot, 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 dot. And like how many vectors here that's like defined as a part of the definition, right? There's n vectors, right? And then it eats a bunch of covectors, right?
Mhm.
It eats like covectors too, right? And then it maps all of these things to R,
Okay.
and then linearly with like all of the things. So you can, so all of these things are linear with respect to each other. And I think I intuitively understand like how that works.
Okay.
But my question was pretty simple. It's how do you eat a map? Like,
Where
you
does
know what
it?
I mean?
Oh, for covector.
Yeah.
Okay. That's a fair question. How do you eat a map?
Like, how does a function operate on a function, or map operate on a map?
I mean, in
get, like,
functional programming, that's like very clear.
right, but like in math, you know what I mean? Like, because we're going to R, and it has to be linear. And so I guess my point was I never saw an example of a 1-1 tensor. I think that would have resolved my confusion, you know, maybe. Like, what does a 1-1 tensor look like?
You're gonna find this example funny, but a matrix. It's a really weird example. So basically, the crazy thing is that if I give you something like a matrix, A, B, C, D, a matrix does many things. It's a many map. It can map a number. Look at this. It can map a number to a matrix.
Yeah.
A squared. It can map a vector to a vector.
Yeah.
It can map another matrix to a matrix.
Yeah.
It can map a covector to a covector.
Wait, it can map a covector to a covector. Can you tell me about
Yeah,
that?
I'm sure you've seen this before, like this kind of matrix multiplication equals. Wait, hang on. Wait. Yeah, that works out. Whatever this may be, blah blah, blah blah. The point is that a matrix let's keep it clear. Let's say that a matrix takes in a vector, right?
Yeah.
And then sends it to a vector. In this case, the vector is itself a map that takes a scalar like A to a scalar, or to a vector, sorry. Like it's crazy. It's like fucking Matrix, or yeah, the Matrix, bro. Inception. No, not the Matrix. Inception. It's Inception shit. Because a matrix in this case takes a function to a function. So maybe covectors are actually better. Same thing with covectors. If this is a covector, yeah, it's a bit of a mindfuck, honestly.
I suppose, but here's my point is,
Yes.
are all covectors guaranteed to have some kind of like in introspectable thing that could be mapped in such a nice way? Like, we just assume that like this thing was you're able to introspect it, and then like, oh yeah, clearly there's a way to map a matrix, you know what I mean? But like, for example, like maybe a covector has like some weird structure internally that you can't map in an easy way. Like, for example, one was given was like the differentiate or integration, right?
Yeah.
How the hell do you map how do you eat integration? You know what I mean? How do you
Yes.
eat it? Can you answer that?
Fucking crazy. But the thing is, these two things answer each other. What does a covector do? It acts on this vector here. What does this covector do? It acts on this vector. Like, it's literally a mindfuck. Like with integration, what do? You act on the vector of that system, which is a function. And then you send it down to a number.
Well, that's what the covector does, right? Yeah, I agree with that.
Yes. So in
And
this
so
case,
in this tensor definition,
what's a
what
matrix?
you're saying that like we use the definition of a covector to generate this map itself?
Hang on. So integration is a covector. So that's just a single example.
Agreed.
If we're talking about a matrix in function land, whatever that may be, like with integration and polynomials, then that's going to be like a level deeper of mindfuck.
Okay, yeah, maybe we should save that for next time. But
Yes. This is like
I'll keep my mind open.
okay, cool,
Um,
cool, cool. But covectors, the classic explanation is to see them as rulers, as measurement devices. Measurement devices are the go-to thing that take a vector and send it to a number. Like if you see a vector out in the wild intuitively, the thing that's going to send it down to a number is by measuring it. So you're
measuring something about it. Yeah.
That was perfect. Yeah. Like this intuition of giving it but know that there's other rulers you could use. You can use a ruler that measures inches, a ruler that measures meters, and it's going to give back like a different thing.
Yeah, I agree. That makes sense. And then like the space of covectors.
Yes.
B star is just like all possible rulers.
Exactly. It's definitely a mindfuck, but it's cool to see.
Yeah, my point was that it didn't sit. The tensor definition didn't just still didn't sit well with me. Yeah, I was not able to see that, but maybe it'll become clearer as we walk through it again.
Yeah. Okay, cool. Yeah, your mind is primed for this stuff.
I'll rewatch the lectures and I'll let you know.
I would be tempted to ask you to explain a basis, but I feel at this point you're completely drained.
I'm pretty drained, but I do understand basis. I mean, I understand basis, but then I did not understand what came after.
Okay.
Because I didn't like watch it fully. Like basis is simple. Basis, it's just like a set of vectors constitute a basis if for all vectors in the vector space there exists one and only one combination of the basis vectors that generate the vector we were talking about. And that definition makes sense to me, because if you set a basis, then that is the set that you're like now going to combine to get to like whatever other thing. In that definition, yeah, and there's only one combination. That means that the vectors in the basis have to be linearly independent, right? You know what I mean? They can't like line up on each other, because then there wouldn't be a unique combination. So I think that definition of basis did sit well with me. Then what came after basis is I forgot.
It was like basis for tensors.
Yeah, okay. I did not get that.
Yeah, that one's like fucking levels deep. An interesting thing that took me like a long time to understand is how this thing that I see all the time is explained using like the very abstract vector spaces. This thing is fucking stupid, but whatever.
Wait, what, that thing?
Yes, this thing is stupid.
What about it is stupid?
It's just dumb, because if we're talking about an underlying vector field, for example, R2, a vector in R2 is not this bullshit. A vector in R2 is literally just a tuple. It's an element of R2. It's a tuple AB.
Yeah.
The reason that we decide to draw vectors in R2 this way is because we assume a basis exists, specifically the basis 1, 0, 0, 1.
Yeah.
And then we express these things in terms of these things. Which is unnecessary choice. Why choose a basis when you can talk about vector spaces perfectly fine without them?
Okay, that does make sense as like a
But anyways, yeah, you're definitely drained at this point. So
okay, but that was fun.
Okay, sick.
I will watch it. I will watch this after the fact on YouTube.
Yeah.
Then I'll cry that I have to clean up this flowery mess after.
Rip.